All right. We have to wrap up something that, normally, oh, you need the screen on. Would you like to see what I'm writing for the next hour? Oddball topic to have right here. Y'all know that college algebra was kind of reordered this semester, and I wouldn't say this is where it makes the most sense. However, it is what it is, and what we need to talk about today are rational expressions and equations. And rational expressions are just quotients of polynomials. Now, what does the word quotient mean in math? You're dividing. So you're dividing two polynomials. We know what polynomials are, just terms x to a power added together or subtracted. So we're going to do everything we did with fractions in basic math, and I don't know, 3rd or 4th grade. We're going to do the same thing in algebra. It's going to be a lot more fun in algebra. But it's my intent to show you how all the processes are the same, so you don't feel like you're learning something brand new. The first thing we learn to do with fractions is to reduce them. And in basic math, we might take a fraction like 6/8 and factor both the numerator and the denominator. We'd factor the 6 into 2 times 3. We'd factor the 8 into 2 times 4. And then is it legal to cancel these factors? To say 2 divided by 2 is just 1. And so 6/8 is the same thing as 3/4. All right, tell me what the difference between my canceling here and what I'm about to say is. Tell me what the difference is. What if I said, well, I can write the 6 as 5 plus 1 and the 8 as 5 plus 3 and then cancel the 5s, and 6/8 is just 1/3. That's the difference, Isaac. These 2's are the factors. I can cancel factors. Factors are held together by multiplication. But I cannot ever in basic math or in algebra cancel terms or parts of terms, things that are added. So that's the first big thing to note. You cannot cancel terms or parts of terms. You can only cancel factors. So the first thing we do on any simplify the fraction problem, whether it's basic math or algebra, we factor so that we can cancel our common factors. One other thing I wanted to write here is, yeah, can't do that. 6/8 is not the same thing as 1/3. So on example 1, there's really nothing for us to do because 2x plus 5 won't cancel. I just wonder if you could tell me whether it would be legal to cancel those 2's and say that this expression just is the same as x plus 5. Why not? Then
Because of the 5.
because that 2 is part of a term. 2x is a term that has 5 added to it, and you cannot cancel terms or parts of terms. You can only cancel factors. So put a big old no by that question mark. If you really want to see if 2 expressions are equivalent, you could eeny, meeny, miny, moe, pick something for x and see if both sides give you the same number. If you let x be 1 on the left-hand side, you would have 7/2. Is that what you'd have on the right-hand side if you let x be 1? No, it's not. So these are not equivalent because I illegally canceled a part of a term. I can only cancel factors. On number 2, it makes me wonder if I can cancel those 2x squares and cancel those 2x's. Would that be legal? Are those x squares terms or are they factors? They're terms. They have stuff added to them. So would it be legal to cancel them? No, you can't cancel terms or parts of terms. You can only cancel factors. So what's the first thing we do to simplify any fraction? Factor completely. All right, now I'm gonna do my factoring fast, just because we've got so much to talk about, and you're supposed to be good at factoring already. In the numerator, there's a GCF. I could factor out an X, and that would leave me a 1 minus X. And I can factor the denominator into X plus 2 times X minus 1. And it's incredibly important to remember to check your factoring. The last 3 or 4 problems on the test are from this lesson. And if you misfactor anything, it's going to totally throw off your answer. So don't go on until you multiply that back together. Make sure it gives you what you started with. Now, I know I can cancel common factors in basic math because I did right here when I canceled those 2's. Really, when I say cancel my 2's, I mean I said 2 goes into 2 one time, 2 goes into 2 one time. I divided numerator and denominator both by 2. Are 1 minus X and X minus 1 the same thing? They're not the same thing. There's a word for what they are. Here the one's positive, here the one's negative, here the X is negative, here the X is positive. That means they're reciprocal is when you flip a fraction. These are opposites of each other. One is just the other multiplied by -1. If I took this X minus 1 and multiplied it by -1, it would become that. So what do you get in basic math when you divide something by its opposite? For example, if you divide 5 by -5, what do you get? If you add 5 to -5, you get 0. But if you divide 5 by -5, you get -1. And the same thing is true in algebra. When you divide something by its opposite, it doesn't leave you a +1, it leaves you a -1. And I didn't realize that next example was going to do the very same thing. Actually, I didn't finish this one. That would equal X over X plus 2 with the negative coefficient, negative X over X plus 2. Could I cancel those X's and say that they just leave me -1 because they're opposites? Eddie? You're right, but you don't look very confident in that answer.
But I have a feeling you're just gonna say the same as you did before.
Exactly, because anything that has stuff added to it is a term. And you can't cancel terms, you can only cancel factors. So every time you're wondering if it's legal to cancel something, just ask yourself, is it a term or is it a factor? If it has stuff added to it, it's a term and you can't cancel it. If it just has multiplication, like this did, then it's a factor and you can cancel it. All right, so I didn't really mean to do the same thing twice. I wasn't thinking when I put both of those examples on here, but this is just something divided by its opposite. Just like 5 divided by -5 or 2 divided by -2. What is something divided by its opposite? Always. Basic math, algebra doesn't matter. The rules of math don't change. Everything just looks a little bit different when you throw some X's in there. All right, that's reducing fractions. Now, what about multiplying and dividing fractions? How do you do this division problem in basic math? No one hands you a calculator. James, were you thinking something? No? Isaac, was that you? I heard a guy's voice, I thought. Maybe it's just a deep-throated woman. Yes. You just take the reciprocal and Brittany, are you the one that said reciprocal a while ago? We're ready for that word now. We're going to take the reciprocal of the second fraction and then change it to multiplication. So 8/15 divided by 6/25 is the same thing as 8/15 times 25/6. Straight across, I think I'd get 200/90, and I could reduce that. But if I cancel my common factors before I multiply, I don't get such big numbers that I have to reduce. So I could write that 8 as 2 times 2 times 2, and that 15 as 3 times 5. I could write the 25 as 5 times 5, and the 6 as 2 times 3. That's called the prime factorization of each number. I factored each number as completely as possible. That's what we do in algebra. Factor as completely as possible. And then all of this is multiplication. I don't have any terms, so it's legal to cancel my common factors. I could cancel this 2 with that 2. And again, when I say cancel, technically I should be saying you can divide both of those by 2 and that'll leave you 1. You can divide both of these 5s by 5 and leave you 1. What about those 2 3s? They're the same thing. Can I cancel them? Why not? They're both in the denominator. You can only cancel factors in the numerator with factors in the denominator. So I don't think I have anything else I could cancel. If I multiply straight across now, this is 20/9, which is what 200/90 would have reduced to if I had multiplied straight across first. Whatever we do in basic math, we do the same thing in algebra. It's just a little bit uglier. So number 4 is a multiplication problem. Can I reduce that 27 and that 18? 9 will go into both of them. Why not? I'm trying to get you to say the right words. Why can't I reduce the 27 and the 18? They're terms. They have stuff added to them. So if I can't cancel terms and I can only cancel factors, what do I need to do? Factor. Well, that's the first thing we're going to do on all of these problems. I'm going to factor, and then I can cancel my common factors. That's 6x minus 27. I could factor out a 3, and it would leave me a 2x minus 9. The first denominator is a monomial. I don't need to factor it. And the second numerator is a monomial. But I can factor a 2 out of the second denominator, and it also leaves me a 2x minus 9. Now, would it be legal to cancel the 2x minus 9s? Yeah. Cancel the whole thing. What about these 2 2's in the same fraction? One's in the numerator, one's in the denominator, but is it legal to cancel common factors in the same fraction? We did up here. That was just reducing a fraction. So we can here. We can cancel those 2's, or say 2 goes into 2 one time. And it looks like all that's left is 3/5x. What if that was 3/6x? Could I divide the 3 into the 6? Yep, because the 6 would be a factor. It would be multiplied, not added, and so I could reduce that if it was 3/6x. All right, number 5 is just a weird way of writing division. You can also call that a complex fraction when you have one fraction divided by another fraction. It's just a different way to write this same thing. So I would still take the reciprocal of the second fraction and change that to multiplication. I'd write it as 3 plus x over 3 minus x times 9x cubed over x squared minus 9. To save us a step, is it okay if we just go ahead and factor that x squared minus 9? That's the difference of two squares. That's x plus 3 times x minus 3. So just like we did in basic math, I multiplied by the reciprocal of the second factor. Do you see any common factors I can cancel? Are 3 plus x and x plus 3 the same thing or opposites? Both 3's are positive, both x's are positive, so they're the same thing. Order doesn't matter when you're adding. 5 plus 7 is the same as 7 plus 5. So 3 plus x is the same as x plus 3. When you cancel them, that only leaves a positive 1. And usually we don't even write down a positive 1. So, how about this 3 into that 9? Can I divide 3 into this 9? Y'all are getting the hang of it. All the heads are going the right way. Why not? That 3 is a term. It'd be okay to cancel the 9 if there was a factor of 3 in the denominator, but I can't cancel a term or a part of a term. So this is 9x cubed over 3 minus x times x minus 3. It is 100% okay with me if you leave that as your answer on the test. You'd have every piece of credit you could have. I suspect that may not be how the answer will be shown to you in my lab, because it really can be written just a tiny bit more simply. Remember when I said 3 minus x and x minus 3 are opposites of each other? If you factor a negative 1 out of one, it becomes the other. If I factor out a negative 1 and just put it out in front of the fraction, then in the denominator, I'll have x minus 3 times x minus 3. And I can write that as x minus 3 squared. Now, anytime I say or, I'm saying either one of these answers is fine, but I want you to understand why this is the same thing as this. They factored out a negative 1 and just put it out front. All right. On the test, you have one multiplication problem and one division problem. And then you have some adding and subtracting problems. And adding and subtracting fractions, why is it more difficult than multiplying and dividing fractions? What do you have to add and subtract that you don't have to have to multiply or divide? Common denominator. Have to have a common denominator to add or subtract. And if you think about it, let's say you were at a party and there were a bunch of large pizzas, but they had been cut into different sizes. Some of the large pizzas had been cut into 12 pieces. Some of the large pizzas have been cut into 4 pieces. Would it make sense to say, I ate one slice of this pizza, it was huge, and one piece of this slice of this pizza, and it was tiny, and try to put them together and say what portion of a pizza you've eaten? You can't say I've eaten 2 parts of the pizza because the slices aren't the same thing. Getting a common denominator is like making all of your slices the same size. So you can say I ate 6/12 of a pizza, that's half a pizza. All right, in basic math, how do I add 2 fractions that already have the same denominator? Say it again. Like 12/16. No, 12/8. You add the numerators and you keep the same denominator. If you had 2 pizzas that were cut into 8 slices and you ate 5 of one of them and 7 of the other, you've eaten 12 of the 1/8 of a pizza. You've eaten 12 pizzas of equal size. And then you can, simplify that. You can divide both numerator and denominator by 4, and you just get 3 halves. You ate 1.5 pizza. All right, another basic math question is this. 3 of these things are the same and 1 is different. Which one's not the same as the other 3? Ooh, because a negative divided by a negative is a what? Positive 1/2. All 3 of these are the same as just the first one. And the moral of that story is if you have a negative in front of a fraction, you can put it in the numerator, or you can put it in the denominator, but you cannot put it in both. That makes sense? All right. So example 6 is a subtraction problem. If that were an addition problem, it'd be just like this basic math. I would add the numerators and keep the same denominator. But I have to pay attention to that negative in front of that. A negative and a minus are the same thing. If I put this negative in the denominator, then my denominators won't be the same anymore. This one will be 3x plus 4. This will be negative 3x minus 4. So whenever you have a subtraction problem, a negative in front of a fraction, 99 times out of 100, you're going to change that to addition and distribute that negative to every term in the numerator. You're going to add negative x minus 1. And now it's just an addition problem, and you can combine like terms. The 5x plus the negative x is 4x. And the negative 4 minus 1 is negative 5. Keep the same denominator. It's just like the very first day of class. If I gave you 5x minus 4 minus x plus 1 way back weeks ago, I would have told you the first day of class the most common mistake is forgetting to distribute that negative completely. And this is the same mistake. Unless I distribute that negative completely, I'm probably going to end up with 4x minus 3 instead of 4x minus 5. So watch out for that. Now on example 6, when I said, whenever you have a fraction that has a negative out front, 99 times out of 100, you're going to distribute that negative through the numerator. Miss Brittany, something's making you frown. Can you tell me what it is?
No, I just didn't hear it when you said distribute.
Oh, so far so
Yeah,
good?
yeah,
Okay. Then number 7 would be the other 1 out of 100 times, because I could change this to addition and put the negative in the numerator, just like I did example 6, but then my denominators wouldn't be the same. I can choose to put that negative distributed through the denominator instead of the numerator, and then my denominators will be the same. I'll have 6 over x minus 1 plus x over, if I distribute a negative 1 through the denominator, I'd have negative 1 plus x. Is that the same thing as x minus 1? Yeah. As long as the x's are both positive and the 1's are both negative, they're the same. So in example 7, I chose to distribute the negative through the denominator to make me have the same denominators. In number 6, I chose to distribute the negative through the numerator because I already had the same denominator. Number 7 would just be 6 plus x. And you could either write the denominator x minus 1 or negative 1 plus x because they're the same thing. Any questions? All right. The next thing is something you probably haven't done in basic math in a long time. And that's if you're adding fractions and you have to get a common denominator, you have to find the least common multiple of all of your denominators. That's a lot of big words. And I did this for you. I knew that we wouldn't have time to do a factoring tree. So I just wrote the prime factors of 168 and the prime factors of 180. You're never going to have to deal with numbers that big. I just want to help remind you how you find the LCM when you have these factored. LCM stands for the least common multiple. The smallest thing that 168 and 180 will both divide into evenly. For example, if I say what's the GCF of 10 and 12, that means what will divide into both of them evenly. What would it be? The GCF of 10 and 12 would be 2. 2 is the biggest thing that will go into both of them. But if I say what's the LCM of 10 and 12, then I'm not talking about 2. I'm talking about 60. They will both divide into 60 evenly. So make sure you understand the difference between GCF and LCM. I'm looking for something that 168 and 180 will divide into. And the way we do that, after we have the prime factorization, we just put in the highest power of each factor. The most 2's that either one has, the most 3's that either one has, the most 5's that either one has, and the most 7's that either one has. What's the most 2's that either one has? 2 cubed is my highest power of my 2's. And what's the highest power of my 3's? Squared. So 3 squared. And what's the highest power of my 5's? Just 5 to the first. And the highest power of my 7's? 7 to the first. So I went ahead and multiplied all of those together for you. It came up to be 2,520. Because the point that I was trying to make was not can you squint hard enough to figure this out in your head, but help you understand that LCM is the highest power of each factor. If that's what it is in basic math, then that's what it is in algebra. Example 8, if these were 2 different denominators of a fraction and I needed to add them, I would have to find the least common multiple. So I factored the first one, I factored the second one, and the LCM has to have the highest power of each factor. So how many x minus 4's do I have to have? The highest power of the x minus 4's. Do I need anything else? The highest power of my x plus 3's. Because I have to have the highest power of each factor. Number 9 has 3 expressions. Maybe I'm adding 3 fractions. So I factored the first one, I factored the second one, I factored the third one. I want you to help me figure out what all has to go in the LCM. Tell me one thing that has to go in there for sure. I heard an x minus 4, and it doesn't matter in what order you write them, but I heard an x minus 4, squared, because that's the highest power of my x minus fours. What else? Because that's the highest power of my x plus twos. Anything else? Also the highest power of my plain old x's.
Do you have to write that in the front?
No, it's the same thing. If you put it in the middle or at the end, it just looks a little bit weird to a math teacher. It's the same thing. Normally, we write our monomials, one term polynomials, before we write our binomials, but no biggie. All right, and number 10. What if I was adding two fractions, one of the denominators was p, and one of the denominators was p minus 4? What would the LCM be? You'd have to have both of them. There's nothing I can multiply by p to make it become p minus 4. Is that right? Multiplying by p by, say, -4 doesn't make it become p minus 4. Those are two different factors. So just like in example 9, we had to have this x squared along with these other factors. On number 10, we have to have both the p and the p minus 4 multiplied together. The LCD is p, or LCM is p times p minus 4. Now notice that I left all of those in factored form. I didn't multiply it out and call it p squared minus 4p. There's a reason for that. We'll see in just a minute. But right now, let's say just leave those LCMs factored. Before we can add and subtract fractions that don't have the same denominator, we have to be good at finding the LCM. And then let's go back to basic math and figure out how we would multiply, or excuse me, add 1 over 68 plus 1 over 180. We found the LCM right here. Same numbers. We found the LCM had to have a 2 cubed, a 3 squared, a 5, and a 7 all multiplied together. So see if you can make sense of the way that I wrote this. 168, right here we said it was 2 cubed times 3 times 7. I just copied that down right here. And 180, we said it is 2 squared times 3 squared times 5. I just wrote that down right here. So what I've done in this first step is I've just factored both denominators, and I left a blank after each term, and I'm going to figure out what goes in that blank. But do you understand that so far all I've done is factor the denominators? All right. The reason I factor the denominators is so that I can look at them. Let me put this LCM right here so I can have it on the screen at the same time. The LCM that we found above. Now I can look at it and say that 168 had all 3 2's it needed, and it had the 7. What did it not have? It needs one more 3. It had 1 3. It needed 2. So it needs one more 3. Anything else? And it's missing the 5. So if I multiply this by 3 times 5, it would have the common denominator. I can't just go around multiplying stuff by 15 whenever I feel like it. Or can I? If I multiply a number by 15, does it change it? Yeah. What's the only number you can multiply times something that doesn't change it? 1. How can I write 1 as a fraction? 1 over 1? Or 2 over 2? Or 9 over 9? Or 15 over 15? If I multiply this fraction by 3 times 5 over 3 times 5, all I'm really multiplying by is 1. But that's what I had to multiply by for that fraction to achieve that common denominator that I had to have. Second fraction, here's what my 180 factored into. Look at the LCM and tell me what it lacks in being the GCF. It needs another 2. It has both of the 3s, it has the 5, it needs the 7. So a 2 and a 7 is what the second fraction needs to make it have the LCD. Well, I can multiply times 2 times 7 as long as whatever I multiply the denominator by, I multiply the numerator by the same thing. So that really I'm only multiplying the fraction by 1, and multiplying it by 1 doesn't change it. So what does this first fraction's numerator become? 1 times 3 times 5? That's just 15. The first fraction is the same thing as 15 over 2,520. What's the new numerator of the second fraction? 14. So 1 over 180 is the same as 21 over 2,520. And once you have the same denominator, you can add the numerators and keep the same denominator and then reduce it.
How'd you get 21 again?
How did I get? I don't know. I don't know. I don't know. Thank you. I don't know what I was thinking. 2 times 7 is not 21, it's 14. Thank you, Chloe. Now, in my opinion, that's a worse basic math problem than all the algebra problems that are on the other side of the page. But I did it to help you understand the steps. Let me just look up and listen for a second while I talk through these steps again, and then I'm going to show you that we use the very same steps in algebra. The steps for adding and subtracting fractions with unlike denominators. We have to factor the denominators completely to find the LCM, and the LCM has to have the highest power of each factor. Once we determine the LCM, we factor the denominators so that we can tell what factors are missing. We factor these denominators, but then left a blank that we went back and filled in. We factored this denominator and left the blank that we came back and filled in. To figure out what to fill in the blank with, we just looked at the factored form of this denominator and say, what does it need in making it have the LCM? It needs a 3 times 5, or I could have said it needs a 15. So I multiply by 15 over 15. This one, what's it missing? A 2 and a 7. So I multiply that fraction by 14 over 14. I got my new numerator. I added, and that will not reduce because 29 is a prime number. But that's the process. That's the process with some pretty big numbers I never want to have to add by hand again. But what I typed for you on the back is those very same steps. And they make more sense when you're looking at an example. If you look at those words and this example, you'll see that we did exactly what those words say. So let's try this on an algebra problem. Example 11, I'm adding 3 fractions, or really subtracting 1 fraction and adding 1 fraction to another fraction. Let's take care of that negative right off the bat. Is there any reason that I would want that negative in the denominator? Would it make it like any other factor? No, it wouldn't. So right off the bat, I put that negative in the numerator. All right. let me number these three groups of, or not number, but letter these three groups of steps, A, B, and C. A has 3 baby parts, B has 3 baby parts, C has 2 baby parts. So let's look at step A. It says factor any denominator that will factor. The only one that would factor is this last one. I could factor out an X. Step 2, leave a blank after each term, because I'm going to come back just like I did here and fill in that blank in just a minute. So that's all we do in step A. Factor any denominator that will factor, leave a blank after each term. If one term is subtracted, put the negative in the numerator. Step B, find the LCD. Well, to find the LCD, you need to look at these in factored form and put in one of each factor to the highest power. So what's the LCD going to be? It has to have the X and the X plus 5. Oh, step 4 says find the LCD and write it down for each fraction. I had 3 fractions, so I wrote that LCD down 3 times. Number 5 was the hardest to put into words. It was in basic math where we figured out what our missing factors were. We just need to do that with algebra. So looking at this denominator and the LCD, what's this one in part A missing? It needs another X. So what can I put in this blank? What can I multiply that fraction by? It has to be X over X so that I'm really only multiplying by 1 and I get an equivalent fraction. Second fraction, what does that denominator need to make it have the LCD? So what do I multiply the second fraction by? I love how you said that. It had to be something over itself because that's 1. What would the third denominator need to make it have the LCD? Well, it already has an X and an X plus 5. So, Chloe, when you shook your head, you didn't mean 0. I don't want to multiply it by 0, but since I can't erase that blank that's printed, I'll just put a 1 over 1 there. I don't really need to multiply it by anything. Step 5, and again, that's the hardest step. Step 6, in basic math, we multiplied that 3 times 5 to get this 15, and that 2 times 7 to get that 14. So that's what we're ready to do here. The X times 4X plus 1, make sure you distribute it completely. It would be a common mistake to forget to distribute completely. Same thing with that -2 in a minute. Make sure you distribute completely. When I distribute this X completely, what's this first new numerator become? Perfect. When I distribute this -2, what does the second new numerator become? -2x minus 10. And the third numerator, 10 times 1 is still 10. Caution you one thing right here. If I had not taken this negative and put it in the numerator, I probably would have had a -2x plus 10 here. It's harder for my eyeballs to remember to distribute it out front than if it were in the numerator. Putting it in the numerator helped me remember to distribute it. And that's all of step B. Step C, add the numerators, keep the same denominator. Well, adding these numerators, I'm just combining like terms. What would I have if I combined all possible like terms in the B part?
4x² plus, no, minus 2x squared. Wait, it's 4x² minus 6.
Minus x, because this is 1x minus 2x is negative 1x. Anything else? No, negative 10 plus 10 is 0. So that's number 7. I added the numerators and kept the same denominator. And then without looking over here, if I just said, hey, reduce that fraction, what would you do next? You would factor to see if you had any common factors. You would factor out an x. That would leave you a 4x minus 1. And then would it be legal to cancel those two x's or not? They're factors. Once you factor them out, they're factors. So that's 4x minus 1 over x plus 5. Now, one thing that, I don't know if it drives all math teachers nuts. It drives me nuts when students say, I understand it in class. I'm like, of course you do. I'm a good explainer. You have to get to the point where you can talk yourself through these steps without having them beside you, because I'm not putting those steps on the test. So what I would suggest on example 12 is, well, let's say the first couple of addition problems in the homework you do with this paper beside you, and then put that paper away and see if you can do a couple more without it. See if you've learned the process, because that's how you do math. You talk yourself through the process. One more example, because this is the hardest thing we have to do today. Step A had 3 parts. Factor the denominator that will factor, leave a blank after each term. If one of the fractions is subtracted, distribute the negative through the numerator. What did I not do here? What important step did I forget? If I don't put that negative in the numerator, I'm going to forget to distribute it completely. I'm going to help you with one more step, and then I want to see if you can follow it. Have we finished step A? We did everything that step A said? Yes. Step B, what's my LCD? One of each factor to the highest power it occurs. Beautiful. X plus 2 times x minus 2 times x plus 3. It has to have all 3 factors. That was step 4. We found the LCD and we wrote it down for both fractions. I want you to do 5, 6, and 7. Steps 5, 6, and 7. tell me what you multiplied the first fraction by. Would that make it become all of this?
Okay, so I was getting confused. So,
Okay,
was.
okay, okay. Let me show you something on the front page, best way to answer that. Here on example 9, when we said it has to have the highest power of each factor, that was an x minus 4 squared, and it was an x plus 2 cubed, but it also had to have this x squared. So here, the LCD had to have the x plus 5, but it also had to have the x. Now, in example 12, we don't have a factor that's plain old x. So it's not gonna have to have a plain old x.
So maybe 4x, so.
Okay, why don't you punt and I'll come back to you, is that okay? Miss Laney, can you look at this denominator in factored form and this LCD that I want to achieve and tell me what to multiply that first fraction by? That's what it's missing. And I like that you said not just x plus 3, but x plus 3 over x plus 3, because I'm trying to make the point that the only thing that's legal to multiply that fraction by is 1. Okay, I'm looking at this and I'm saying, what does this have that this does not have? Okay, then I bet you can answer this for me. What does this have?
X plus 2.
Yes, it has the x minus 2, it has the x plus 3. What it needs is the x plus 2 over x plus 2. Did that help, Miss Sydney?
Yeah, that.
Okay. Again, the only thing you can legally multiply is by 1. All right, Mr. James, would you tell me what this first new numerator became?
Plus 12.
Yes, 4x squared plus 12x, because you remembered to distribute that 4x completely. And Miss Barbara, can you tell me what the second new numerator became? And what is that when you distribute the negative 2? Right. Okay, Miss Barbara? Okay. And so what am I ready for now? I guess that was step 6, multiply to get my new numerators. I'm ready to add the numerators, keep the same denominator. Adding the numerators is combining like terms. 4x squared, a positive 12x minus 2x is positive 10x. And I don't have anything to combine with my minus 4. That okay? What do I need to do in order to see if that will reduce? I need to factor it. And the first step in any factoring is GCF. That numerator has a GCF of 2. Anytime you factor, check your factoring. Then, if I factor that further, it's the hard kind of trinomial. Hard kind of trinomial is where I have to multiply the constant times the coefficient, 2 times 2. And ask myself, are there factors of 5 that have a what? That last sign being negative means I want factors of 2 that have a difference of 5. Are there any factors of 2? I'm sorry, factors of 4 that have a difference of 5? Do they have a difference of 5? Difference means what? Subtract. So they don't have a difference of 5, they have a sum of 5. And Miss Emily, that's why I know this won't factor. There aren't any factors of 4 that that subtract to give you 5. So that's it. In my opinion, 2 hardest things that we're covering today, I don't think the reducing, the multiplying, and dividing is difficult as long as you can factor. Adding and subtracting, as long as you have the same denominator or just opposite denominators, that's pretty easy. But you can see that this process was kind of intense. I will tell you, the more neatly you write it, the higher the chance you'll get the right answer. When you're doing your homework, do it just like we did this. Copy down the original problem and then number your steps, A, B, and C. If it takes you more than step A, B, and C to get the right answer, or if you're writing sideways on your paper, you're probably confused. And then there's one other thing we need to talk about, and that is solving equations with rational expressions. What's the difference between expressions and equations? What makes Right, and equations do. Expressions are like phrases in English. They're not complete sentences. You can't say if they're true or false, because it's just a part of a sentence. If you have an equation, though, you have a complete sentence, and you can find the value of x that makes that equation true, or makes that sentence true. So you really have to squint hard and understand the difference between adding expressions and solving an equation. Because what you do in those 2 processes is different. What we just did in examples 11 and 12, we were adding. And here we're adding. When I'm adding, I have to multiply each expression by 1 to make both fractions have the same denominator, and I do not cancel out the denominator. So you can see this example looks just like 11 and 12. It's easier because it doesn't have x's in it. But I'm multiplying each fraction by 1, and I am not canceling out the denominators. Solving equations is different. My goal in solving this equation is to somehow get rid of all the fractions. I want my answer just to be x equals some number. That number may be a fraction, but I don't want my second line to have fractions anymore. Well, when I was adding fractions, I said the only thing you can multiply by a fraction or any number without changing it is 1. But if you have an equation, you can multiply both sides by anything you want, as long as you're not multiplying by 0. I don't have to multiply the first fraction by 3x over 3x and the last one by 2x over 2x. I can look at all 3 of those and say the common denominator would be what? What will 2 and x and 3 all divide into evenly? 6x. I can multiply all 3 terms by the LCD. So here I multiplied by 6x over 1, 6x over 1, 6x over 1. I multiplied every term by the LCD. And when you get home tonight, before you start the homework, I want you to look at these 2 examples again and say to yourself, expressions don't have equals. I can only multiply each fraction by 1. Equations do have equals. I can multiply every term by the whole LCD. And what that allows me to do in this first term, since that 6 is a factor, it's multiplied by x, not added, I can say 2 goes into 6 3 times. And that first term just becomes 3x, no fraction anymore. Second term, since that 6 is multiplied by x, I can cancel the x's and say all that's left of the second term is 1 times 6. And on the right-hand side, I can say 3 goes into 6 2 times. And all that's left of the last term is 1 times 2x, which is 2x. And then I'm just solving a little baby first degree equation. And what do I call a first degree equation? Linear. That's a linear equation. I just subtracted 2x from both sides, subtracted 6 from both sides. But you must understand the difference between these two processes. One is just expressions, one is equations, and that changes what you can legally multiply by. Still, we're doing all right on time, pretty good on time. One big caution before we look at these last 2 examples. When you clear fractions out of an equation, you must check to see if any of the proposed solutions make any of the original expressions undefined. And what do I mean by that? What makes a fraction undefined? Give me an example of a fraction that if I saw it, I would write, that's undefined. 7 over 0 or 10 over 0, anything over 0. I cannot allow that to happen. So this equation, in example 13, if I were solving it, and let's say I came up with blah, 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 x equals 5, could I use the 5? Could I let x be 5 in the original equation?
Yeah.
No. So if that's what I come up with at the end, I'm just gonna have to mark it out. But I made myself a note here, so checking to make sure I didn't forget, I can't use 5 as a solution. What's the LCD of all the fractions? Well, the LCD is x minus 5. So I'm going to multiply all 3 fractions by x minus 5 over 1. Multiply all 3 terms by the same thing. Because what that allows me to do in the first term, I can cancel the whole x minus 5s. I couldn't cancel just the x or just the 5, but if I'm canceling the whole factor, that's fine. And on the right-hand side, same thing. I can cancel the whole x minus 5s. So what's left of this first term? Yeah, 3x times 1 over 1, but as simply as possible, that's just 3x. What's left of the second term?
Oh, yeah, I guess it would be x minus.
You could keep the 2 outside parentheses with the x minus 5 in parentheses, or you can go ahead and distribute that too. I would just go ahead and distribute. And what does the right-hand side clean up to? Just 5. 5 over 1 is just 5.
What about the 2 times the 1?
Well, that's a great question. Any whole number can be written as over 1. 2 is 2 over 1. So when I multiply the 1's in the denominator, I could put this over 1, but I just don't need to. All right, combining like terms and adding 10 to both sides, I get 5x equals 15, so x equals 3. Now, is there any reason that I cannot use 3 as an answer? It doesn't make any of the denominator 0, so it's fine. I did go ahead, because I'm OCD, and type out the check for you. Check it back into the original equation. I put 3 in place of all of those x's, and sure enough, came up with -5 halves equals -5 halves. Since both sides are equivalent, my answer is x equals 3. All right. I'm gonna be real honest with you and tell you that example 14 is almost identical to the last problem on the test. It's just a little bit harder than example 13. Steps are the same, it's just uglier. I factored, the only expression that will factors into x plus 2 times x plus 3. So what's the LCD? It has to have the x plus 2 and the x plus 3. And I'm gonna write that right here. X plus 2 times x plus 3 over 1 is the LCD. So I multiplied the first term by that whole thing, the second term by that whole thing, and the third term by that whole thing, so that I could cancel out all the denominators. That was the purpose of multiplying by the LCD. So in the first term, the x plus 2's cancel. Go ahead and distribute that x and tell me what's left of the first term. X squared plus 3x. In the second term, the whole LCD cancels out, and all that's left is 2. And on the right-hand side, the x plus 3's cancel, and all that's left is 5x plus 10. I think what I meant to write there was before I distributed. You can tell that that's what I meant to write, so that when I distribute, I get this. And when I combine like terms, hey, what kind of equation is that? Second degree. It's a quadratic equation, so I have to get it in standard form. I have to factor it. I have to set each factor equal to 0, and I come up with 4 and -2 as possible solutions. Why am I just calling them possible solutions? Oh, I can't use -2 in the original equation. That'll give me 0 in that first denominator. It'll also give me 0 in the second denominator. But I can't use the -2. So 4 is my only solution. Now, I want y'all to do better on test 3 than you have done on a college algebra test all semester. Here's what's going to help you do that, and I have 7 more minutes to talk, so hang with me. You remember how I always give you this review, and this review compares the problems on the practice test to what lesson they come from, what the objectives are, and these objectives, they're the same thing on the test. On the test, I think that's number 1, and this is number 2 and 3, and that might be 4 and 5, but that's exactly what the directions on the test say. Now, because the reason I had you to do assignment 14 and 15 on paper is there weren't good conic sections and polynomial functions for you to graph in my lab. It only gave you multiple choice, and practicing multiple choice does not feel like the real thing when I give you a problem on the test and it's not multiple choice. Do y'all wanna go, or are you interested in me telling you how to do better on this test? So in addition to doing these problems, whose answers are in the back of the e-text, I would redo assignment 14 on paper and assignment 15 on paper, because that's what it's gonna look like on the test, not a multiple choice something. So don't just do this practice test and go, oh, I'm ready. The test has no multiple choice questions. Redo these two assignments on paper. I've corrected them on your paper, so you have all the right answers. Now I'm gonna stop the recording.